All right. Well, I will begin. That worked? Oh, cool. All right, I'll begin. Dear Father, we thank you for this day. I thank you for these students. Just asking you to again guide our steps. Help us to learn a little bit more about your creation together today, Lord. In your name I pray, Lord Jesus. Amen. You guys have any questions about anything in particular? I could show you another example of something we've already done if you'd like. If there's anything in particular you guys are hung up on. Hand in your solution to the extra credit problem, if you will, the bonus problem, like hand it to the middle aisle and I'll pick it up there. So, well, if no one has a particular question, I'll just dive into an example then. So let me just hypothetically do another example of potential energy. So you're given plot of potential energy U. All right, here it is. Let's suppose our potential energy function looks something like this. All right. So here's X, and we're plotting potential energy. Then, you know, we can discuss what are possible motions in that situation. All right. So, is that all of my? This is all my bonus problems. All right. I'm assuming this is it. Thank you. Thank you. I got him. You got him. Okay. Cool. Thank you. Thank you. All right, so then we can look at different things. Like, for example, what if your energy level? Yowzers! What if your total energy was about here? All right, let's call that E1. Then the question is, what motions are possible if that's the situation? All right, so remember that the total energy is equal to what? The total energy is equal to 1/2 mv squared plus the potential energy, which is a function of x, right? So the thing to keep in mind conceptually with this and the plotting idea is that this is at least 0, right? Like you can't have negative kinetic energy. So that's very limiting. Once you're also given a potential energy, right? So if we're looking at the potential energy here, right? And this is my energy E1, then that means that the motion has to be where your total energy is above the potential energy plot. So like here, right, over here, these are the possible motions. So if your initial position was, say, like right here, right? If your initial position was at x1, what would happen with your motion? You'd be stuck in what's called this potential well, right? Your motion would just be going back and forth, or forth and back, like that. Be stuck between these two, you know, sort of bounding positions. This would be, say, x2. Basically, you'd be stuck between x2 and x3, like that. All right. On the other hand, if your initial position was over here at x5, then either your motion is rightward, in which case you're going to reach that minimum position of x6 here, and then you turn around, right? Or what would happen is you'd have an initial leftward velocity and you just never rebound. You just keep going and going. Assuming that, you know, assuming that this graph doesn't like turn back up again or something, right? So now an interesting energy level is perhaps given by E2, something like here, right? If you just touch on the top of here, so if this is energy E2, right? If that was E2, then this right here is known as an unstable equilibrium. So let me contrast that. There's down here, this is a stable equilibrium. And what that means, like conceptually, is that if you had a particle there and you gave it a little push, what would happen is it would just oscillate close to that point. The motion would be really close to there. It wouldn't spiral off anywhere or anything. On the other hand, if your initial state was like up here, this is an unstable equilibrium because you just don't know what's going to happen if you have a particle that's in this kind of situation and you give it a little nudge. What could happen? Well, either if you give it a nudge to the left, it's just going to spiral off. I mean, it's just going to float off to a minus infinity that way, right? On the other hand, if you give it a push to the right, it's going to bounce over here and back, right? So if you add some friction to this and your energy decreases, then it gets a little bit more interesting. See, because if there was some friction involved, then your energies would be decreasing. And then instead of staying at energy level E2, you'd kind of like, if you were given a shove this way, then you just keep going, slowing down eventually to velocity 0. But if you're given a shove this way, then you'd end up in this potential well where eventually you'd drift down here to this stable equilibrium. So I'm sketching for you guys this concept of energy analysis. And so listen, the question I ask on the test, it's really not that complicated. All you have to do is understand what the potential energy diagram is for the force that you're given. You graph it, or you're given a graph of it, and then you think about where can I be such that the total energy is larger than the potential energy, and that pretty much tells you what the possible motions are. So let's see, what else can I tell you? Well, remember the context here is what? F? The force is what? Minus du dx, right? This is the force. So if you're given the potential energy diagram, can you tell me which way the force is pointing at a given point? So you guys tell me. At x6 on my picture, force points which direction? See, here's x6. Here's a plot of u. Which direction does the force point? What did you? Taylor gave me a hand signal. Well, you're 50-50, right? So it's either left or right, right? Let's think through it. So right there at x6, the function's increasing, right? Du dx is increasing. That means what? Du dx is positive. But we put a minus here. So that plus changes to minus. The force is, you're right, the force goes left. And on the other hand, if we look at, say, at x2, the force points what? At x2, the potential energy is decreasing, right? Which means what? The derivative is negative, so you have minus a minus, which is plus. So the force is to the right, where the potential energy is decreasing. And that is consistent with the story I was just telling you about how the motion's bounded, right? So the force is to the right at x2, right? So the particle comes over here, the force is to the right, it pushes it back. And then the particle travels over to x3. The force is what? It's leftward over there, it pushes it the other way, and the force keeps shoving it this way and that way and this way and that way, and stuck between this, bouncing back and forth. What can you tell me about equilibriums? What are those points as it relates to the force? How about an equilibrium? That's where du dx is what? 0, which means the force is 0. So equilibrium points are places where the force is 0. The force being 0 could either indicate a stable or an unstable situation, depending on whether or not you're at the top or the bottom of a potential well. That's it. All right, that's it. So do you guys have any more questions about? Yep, yes, sir.
Can you give an example of given force field and position function, finding whether or not it's conservative.
Oh, well, that's a long example, but I can try. So here's a force field. Let's say xy equal to, I don't know, x squared plus y and y squared plus x. And I'll do two-dimensional here. So my question is that a conservative force? All right. So the very laborious way to do this would be to find two different paths, right, and to calculate the work done and to compare. And if they're different, then by the theorem we come to last time, there would be path dependence, therefore they're not conservative, right? So like the theorem that I'm mentioning is this, which I probably should just write out for us. If f is conservative on, let's say, a domain D, which is a subset of R2, well, let's say Rn, and typically we're thinking n equals 2 or 3 for us, right? Then the following are equivalent. Number one, the definition. F is equal to minus the gradient of the potential energy function. That's characterization number one. Our definition, the conservative force means you can write it as the gradient of the potential energy function times minus. Number two, for any pair of coterminal paths, C1 and C2, the work done along C1 is equal to the work done along C2. And I should really be more clear, paths inside C, inside D rather. So the picture is D looks like this, whatever. I mean, I'll just draw D as a rectangle just to be boring. You've got two paths, right? And you go on C1, you go on C2, you get the same work. This is path independence. So conservative force over some domain, it's path independent. The work done is path independent over that domain. Another one I haven't talked about yet, but I should, is that and we use this symbol here, usual for this. For all loops, C inside D. So if you can show that the integral around any loop is 0, that also gives you conservative. All right. So going back to you asked me for an example, Sam. So let me go back to this one. This is really the important calculation that I think is most of your homework this time is finding potential energy for a given force, right? How do you do that? So for this one, can we do it? We're trying to calculate partial u partial x equal to what? Minus x squared minus y. And we're trying to find partial u partial y minus y squared minus x, right? For this one I just made up. So can you guys tell me what's the u? What's that? Negative 2x minus, I think you're differentiating. So what would u equal? How about minus 1/3, right? Minus 1/3 x cubed minus xy plus c1, right? And if I integrate the other one with respect to y, I get minus 1/3 y cubed minus xy plus c2. So if I look at both of those, tilt my head and squint, I can see, aha, my potential energy should be minus 1/3 x cubed minus 1/3 y cubed. I just need one copy of minus xy, like that. And then, of course, I can add a constant, a genuine constant over here, like that. This would be the potential energy. This would be the potential energy for this given force. Now, going back to your original question, could I calculate the work over a couple different paths in this situation? Now I'm exactly where I want to be to calculate the integral of the work done by this force, because I don't have to actually do the line integral. I can instead use the potential energy function to calculate the work done, right? So like, if my path goes from, say, I don't know, 0, 1 to over here, what is that? I don't know, 4, 2, let's say. Use your imagination. There we go, 4, 2. What's the work done by the force over this path? The work done, right, over that path would be minus u of 4, 2 minus u of 0, 1. Whatever that works out to. Then you plug the numbers into the formula and take the difference. That would be the work done. I won't actually do that because you guys could do that, right? You guys know how to plug numbers into a formula, I think. Yes? Okay. Well, I've got minus a minus, so this would be, 1/3 64 plus 1/3 of 8. 4 times 2 is 8, so plus 8. And then minus, well, rather plus, but I've got, so x is 0, so I drop that. So it's just the minus 1/3 1 cubed, I think. So for what it's worth, that would be the value. 64. Again, you guys are fishing me into this. I have minus the change in the potential energy here. That's what I'm writing. I'm writing minus the change in the potential energy. So I'm doing the change in potential energy is u of the final point minus u of the initial point. So, yep. Oh, no. After you find the potential energy, you're done. You find the potential energy here, it's conservative. Like, that proves it's conservative from the definition. If you can find a potential energy function for your force, it's conservative. That's what it means.
How do we know it's not conservative?
You try to solve these equations, it goes badly. It's impossible to solve them. Or you do 2 different paths and you find different work for the 2 different paths. I can derive another theorem for you if you'd like. There's a 4. But, well, let me not do that, actually. I'll save that for calculus 3. So, the other thing that we know is if you take the curl of the vector field, if it's 0 over a simply connected domain, that suffices to prove that it's conservative. But I don't really want to be talking about simply connected. I saw that. You're in big trouble, mister. See, so it's simply connected. I mean, what is simply connected? It means there's no holes in it, basically. What's a curl? Well, the curl is a combination of the cross product and the partial differentiation. So that would be combining 2 things that you don't entirely understand, right? So let me not do that at the moment. We will talk about the cross product in here before too long, though. Anyway, other questions? Yeah.
Why is it minus xy instead of minus 2xy?
Why is it? Because I only need one of them. If you partial differentiate this, you get that with a minus. Right? The partial derivative of, this term, right? If I partial differentiate with respect to x, I get minus y, right? If I partial differentiate with respect to y, I get minus x. So it produces both this and that at once. I don't need 2 of them. One of them will do. Yeah.
So why is partial u partial x negative x squared
That's because we define the force to be minus the gradient of the potential energy. Now, if you're also taking calculus 3 right now, I don't know if you are or not, but if you're such a person, in there, physicists, listen to me, mathematicians don't care about this. They only care about the math, so they always write like this. And in that situation, you just set little partial f partial x equal to the x component, little partial f partial y equal to y component. There's no minus. We put minus in everything because we're interested in energy. And yeah, I mean, that does cause some confusion, personally for me, as I apply these things, because I have to keep track of that minus sign and track it. But the good thing is, for us, that that the total energy is potential energy plus kinetic energy. If we didn't put that minus in, we'd have to say that the total energy was kinetic energy minus potential energy, which would be weird. So we put the minus in so we have a plus in the energy formula. It is, at the end of everything, just a convention, though. That is true. Other questions? Would it be good for me to do a one-dimensional example, maybe? Let's do that, yeah. So the force not being conservative, I think I would have to go to, I would have to do something like, something really complicated and probably a little bit out of bounds to make a one-dimensional force not conservative. Like a one-dimensional force, if it's a function of x, it's going to be conservative. The question is rather whether or not you can actually find the antiderivative, because that's the only thing really keeping you from doing it. So if I have f of x equal to, I don't know, alpha x to the 6th minus beta for appropriate constants alpha and beta, what would the appropriate constants look like? What are the units of beta? Newtons, right? What would the units of alpha be? They better be newtons over meters to the 6th, right? So I'm throwing this comment in here to make up for all my sins. My transgressions are many. I have been doing many examples without units, and you'll forgive me for that. Whoa, my shoulder hurts all of a sudden. That's not cool. Anyway, so my question here is, can we calculate the work done from x1 to x2? What's the work done? All right, so we do what? The work is the integral from x1 to x2 of f of x dx, yeah? So in this case, that's x1 to x2 of alpha x to the 6th minus beta dx. We can integrate that. What do we get? Alpha over 7 x to the 7th minus beta x, right? Evaluate that from x1 to x2. You get yourself a alpha over 7 x2 to the 7th minus x1 to the 7th minus beta times x2 minus x1. All right, great. So there you go. That would be the work done for this one-dimensional force from x1 to x2. We just integrate. Simple as that. What if instead of that way of thinking, we wanted to calculate the work done using potential energy? What's the potential for this force? So that was A. B. Find potential energy for force. So that would be what? F equals to minus du dx. And what could you guys tell me? What would the potential be here? Looks like minus 1/7 alpha x to the 7th. I think plus beta x will do it. You can add a constant, right? But I'll just, for the sake of convenience, put the potential energy to be 0 at 0. We always have this freedom to adjust the potential energy 0 to be where we like it to be. Well, always is a dangerous word, but I think that's it. So if we know the potential energy is this, how would you calculate the work done using potential energy? Remember, the work is equal to minus the change in the potential energy. So that would be minus u of x2 minus u of x1. I factored the minus out. I mean, that's u of x1 minus u of x2, if you like, right? Which then, if you just plug x1 and x2 into the formula, we just derived it. What do you get? Where was I? Oh, right there. So that gives me minus 1/7 alpha x1 to the 7th plus beta x1 minus a minus gives me plus 1/7 alpha x2 to the 7th. Let's see here, minus beta x2. And I think if you look at that, right? If you look at this and you compare it to what I have over here, you should see that they're equal, right? So, like, as a point of calculational efficiency, if I don't force you to find potential energy for the one-dimensional problem, if you're just interested in the work done, what should you do? I think you should just integrate, right? Because if you do the potential energy, then you kind of have to add the minus for the potential energy, and then you end up taking it back again because of this theorem, and hopefully you get all your signs right. But if you're like me, working on that problem in your homework earlier today, I got really confused because I forgot one of the minuses somewhere, and then it all blew up in my face. But anyway, so I hope that helps you. All right. On the other hand, for 2 or 3-dimensional problems, when you're calculating the work done by a variable force over an interesting path, definitely finding the potential energy as a function of x and y or x, y, and z is super useful, right? Yeah. Okay. As usual, one-dimensional problems are nicer, right? Let's look at something more interesting. Gravity. Let's talk about gravity. So, Newton's universal law of gravitation, what is it? So we will not use the full force of this for most of what we're doing, but I'm just throwing it out here because I want you to understand the grown-up version of this, if you will. And so here it is. If I have mass 1 here, right, and I have mass 2 over here, all right, and I have a common origin, let's say here. So R1 points to M1 and R2 points to M2, like that. Okay? Then I can define a displacement vector from one to the other. Let's say like this. I'll call that script R. So script R would be what? It would be R2 minus R1, all right? Newton's universal law of gravitation says that the force of gravity is attractive between masses like this, and the force of attraction is inversely proportional to the distance which separates them. So the force due to gravity is simply equal to minus big G M1 M2 divided by little script r squared script r hat. Another way of writing this formula would be this. This is equal to minus G big M1 M2 divided by script r cubed times script r vector. So here, let me draw a picture. This force is the force acting on M1 due to the gravity of M2 is what I'm talking about, okay? What's the force of M2? What's the gravity from M1 on M2? See here's the force of gravity this way, yeah? This is the force I'm talking about right now, this force right here. Well, the force of the gravitational force on 2 due to the attraction of 1 is equal and opposite. They come in a third law pair. See? If you were to talk about the force of gravity M1 generates on M2, it'd be the same magnitude but the other way, like this. Right? So minus F. All right. Now, for the most part, the gravity we're interested in is what? It's a much sillier picture. Earth, yeah. Oh, yeah, sorry. Sphere. Earth is a sphere, roughly speaking. Oblate spheroid. Sorry. Not flat. Okay, so anyway, so then there's M1 is like here. All right. So the picture is much more boring. Essentially, to a good approximation, we can put the origin, we just put the Earth at the origin. That we put the center of the Earth at the origin of our coordinate system, all right? And in that context, this distance right here is what is this distance? This would be the radius of the Earth, right? And then mass 1 up here, that's what we call altitude, h. M1's up here. Right? And of course the force of gravity is attractive, right? And you know what it does. We've all experienced this, right? Like this. So what's the formula then for the force of gravity here? So the force of gravity is equal to big G M1 mass of the Earth divided by what? The radius of the Earth plus h quantity squared, right? And what's our typical coordinate system? What do? We think about y hat pointing downward, right? So, I mean, anyway, this is directed towards the center of the Earth. I can say that without math, right? Directed down. We can just say directed downward, yeah? This is the force of gravity according to Newton's universal law of gravitation. It depends on the mass of the Earth and also the radius of the Earth in this way, right? So, anyway, then the question then you might ask is, and then let's see here, if I set R1 equals to 0, then the mathematics I'm doing over here just becomes F is equal to minus G M1 M2 divided by, well, we could say R2 equal to 0 and R2 equal to R, okay? If I make these special notational choices, then I have minus GM1 M2 divided by R squared R hat. So there's a nice notation for the force of gravity. So is this a conservative force? I could also rewrite this as minus GM1 M2 divided by R cubed R hat, R vector. In other words, F is equal to G M1 M2. I'll put a minus GM1 M2 out front. That's an ugly constant. Whatever it is. And then you've got times the vector x over R cubed, y over R cubed, z over R cubed. We proved the other day that partial x partial r was what? Do you guys remember this? Partial x partial r? X over r, right. And likewise, partial y over r, partial y partial r was y over r, right? And so forth. So let me continue this calculation where I've got a little more space. Notice that if we do, let's see, what would partial x of 1 over r be equal to? We can do the chain rule, yeah? So the chain rule says I differentiate the function, and then I multiply by the derivative of the inside function, so it's a reciprocal, so that's minus 1 over r squared. Then I've got partial r partial x, but you guys just told me that was x over r, right? So this is really minus x over r cubed. Hey, if I brought the minus over here inside, what do we got? If this works for x, it works for y and z too, right? So like partial y of 1 over r is minus y over r cubed. Partial z of 1 over r is minus z over r cubed. So what I'm saying is that if I put my, if I make the circled choice right there, my force, which is, is gm1 m2 times what? Times, well, apparently, partial x of 1 over r, partial y of 1 over r, partial z of 1 over r. That's what we're up against. Well, in other words, the force of gravity is exactly the gradient of a particular function, right? This is g m1 m2 times the gradient of what? The gradient of the 1 over r function, yeah? That's the gradient of the reciprocal of the spherical radius. And then putting this all together, you can rewrite this as minus the gradient of what? Of minus g m1 m2 over r. So in short, the potential energy as a function of r, given my circled choice over there, is equal to minus g m1. Well, let's be honest, we're talking about mass of the Earth divided by r. This is the formula for potential energy as a function of the distance from the center of the Earth, where I have assumed that the potential energy is 0 at infinity. So if I wanted to, if I wanted to make the potential energy like 0 at the surface of the Earth, what should I do? If I want to make the potential energy 0 when r is equal to re, what constant should I add here? If I want to make u of re, the radius of the Earth, equal to 0, what I would want to do is just add plus g m1 me over re. If I do that, then these cancel, and now you've got the potential energy 0 on the surface of the Earth. All right? Do you guys remember using this in high school physics? Sort of? Maybe, maybe not. I mean, it depends on how things went. I don't think this is what usually gets used. Something much simpler usually gets used for gravity's potential energy, right? Because what's usually the case? We're near the surface of the Earth, right? And near the surface of the Earth, we can get away with something much simpler, right? So if you take this, right, you're looking at u of the radius of the Earth plus the radius of the Earth Don't know how that happened. All right. It's all good. Although you guys know I'm easily distracted, so this is on you. Anyway, okay, so continuing. I'm trying to get to an easy example before class is done. I know this is a little bit intimidating at the moment, but so if we look at the potential energy, it's really, think about R is equal to the radius of the Earth. See, R is the radius of the Earth plus the altitude, right? So what you can do is you can Taylor expand this. You can look at U of the radius of the Earth plus the derivative of the potential energy at the radius of the Earth times h plus higher order terms. This, well, anyway, so I don't want to talk about all this today, but we'll have to come back to this later, okay? Let me just say that. We'll come back to this. We'll return to this later. And there's a couple reasons for that. Number one, a lot of you are in Calculus 2 right now. You haven't quite got to the idea of a Taylor series yet, right? So I should hold off on that, for one thing. The other thing is, there's a little bit easier way just right now to do it. So we have what? F equals to, what's the force of gravity if we're working in xy coordinates? What do we say it is? It's what? It's 0 minus mg, right? If we're talking about y being up and down, x being left and right, right? So if that's the case, what's the potential energy due to gravity? So this is equal to what? Like minus partial u partial x minus partial u partial y. What's the formula? U equal to what? Yeah, well, now that's high school showing, right? So mgy, right? So yeah, mgh is what we usually use. Fair enough. So yes, and of course, you may recall this as potential energy is equal to mgh. Totally agree. That's oftentimes our notation here. But here, I'm assuming that y equals to 0 is where potential energy is 0. All right. Now, there's a little bit of daylight. There's like a little bit, like maybe there's like a lot of daylight between this formula and that formula, yeah? But they are the same formula. This right here approximates to that. If I really should put an M1 here for conceptual linkage, but yeah, these are not disconnected stories. It's just that as long as you're close to the surface of the Earth, you can use this very simple mgh or mgy formula for potential energy. But if we're dealing with motions which are like our altitudes of say more than 10,000 meters, then you start to be inaccurate if you just use this formula. You have to use the formula over here to actually account for the dependence of the force of gravity on altitude, because it does decrease. If you go back to the, this formula, as the radius gets further from the Earth, gravity drops off, right? Eventually, the gravity of the Earth goes to 0 if you're far enough out. It doesn't always stay mg, right? Right? There. Okay, so let's work a problem then with our newfound potential energy due to gravity problem. So let's see here. Example, what am I on? Let me put this, I've left this hideous top hat up the whole time. I feel so dirty. Ugh. What example am I on? 5, 6, 7? 4. All right, here we go. This problem would have been an absolute pain before. You've got Mr. Top Hat up here. He shoots a gun. He throws a watermelon at angle theta. There you go, just in case. I don't want to trigger any of you with my discussion of guns. I know we're all just waiting to be offended at any moment. Maybe not you guys, but society in general. And kids can't just play with airsoft guns like they like to at a mall sometimes without getting in trouble. It's here I heard about. Who goes to the mall with airsoft? Like, so my wife was telling me there's like kids with like AR-15 style airsoft guns like running around the mall. It's like, That just sounds like a good way to get shot. Like, it's just not. Anyway. So here's the question. The question is this, or the task is this. Show the speed the bullet hits the ground. I'm sorry, the watermelon hits ground is independent of theta. This is in the notes for the kinematics. This is worked out. It involves a complicated canceling of sines and cosines and such through the kinematic equations. It's pretty cool the way it works out. It's stupidly simple now that we have now that we have energy. So what we can say is if there's no friction, so ignoring friction, because otherwise it's not true. So ignoring friction, energy is conserved, right? So characteristic, there's some height of the building we start with, right? So what we can say is that the energy at the beginning, right? Energy initially is equal to energy finally. It's a conservative process because all of the forces involved are conservative. The only force involved, gravity, right? It's projectile motion. And as I was just trying to show you, gravity is a conservative force, whether or not you approximate it close to the surface of the Earth or if you do the real thing, right? This real stuff we'll need later. We'll come back to this later. This is for the satellite motion at the end of the course, okay? Anyway, so what do we have here? The energy initial is potential energy at the start plus the kinetic energy at the start. And at the end, you got the potential energy at the end plus the kinetic energy at the end, right? So what's the potential energy originally? So we're throwing a watermelon, right? So we have initial potential energy, m, g, h. What's the initial kinetic energy? It's the speed with which we're throwing the watermelon, right? So whatever speed you throw things with, right? So like plus 1/2 mv naught squared, right? What's the final potential energy? 0, yeah. 0. What's the final kinetic energy? Well, I don't know, but it's 1/2 mvf squared, right? Solve for vf. What do you got? Square root of gh, rather 2gh plus v naught squared. There you go. In fact, it's better than I said. It's not only that the final speed is independent of theta, it's also independent of mass, right? Despite, as I've told you, TV commercials continued pressure on us to understand fatter people to fall faster. It's not true. You know, if you took a little watermelon and a big watermelon, you'd hit the ground with the same speed for the same throw. Of course, that's not entirely true because there is such a thing as air friction, right? And the air friction is something like proportional to the surface area. And the way surface area and volume are proportional it's not linearly, right? It's a more complicated interaction there. That's why you get like, you know, better efficiencies from like larger boats because the surface area doesn't increase as fast. Like if you have a larger volume, you have to proportion less surface area, right? So you can do better against the friction of the water with a larger boat. There are efficiencies to be found there. Anyway, so that's that. So listen, we're going to do lots of stuff like this next time, okay? That's my plan. I was going to do that this time, but I think it's better to do some problems that are like your homework. So what's on the next homework past the one you're doing turning in Wednesday are problems with planes and pulleys and all that. That's mission 5. So just so you know where we're going. Mission 4 is mostly math, I know. So sorry about that. I'm not sorry. Wait a minute. I'm not sorry. All right, see you guys.